All right, in Calculus 3.7, optimization problems. I'm going to solve applied minimum and maximum problems today. So this means it's story problems, y'all's favorites. A manufacturer wants to design an open box. That means it does not have a lid. Having a square base and a surface area of 108 square inches is shown. What dimensions will produce a box with a maximum volume? See, a lot of these questions are going to be like, I want to have a minimum cost of my company. I want a maximum profit, maximum volume, minimum surface area, or minimum amount of materials. So these are the different types of questions that are the real world based. So with this picture, the way it's drawn, the area of the base would be x squared. The area of this face over here on the right would be x times h, and I have 4 of those going around the sides. So we were talking about the area, and we're talking about the volume in the story. Again, it's a no lid. We know the surface area is 108, and we want a maximum volume. So I do know I need a volume formula. I am given the area, so I went ahead and went with an area formula as well. X squared plus 4xh equals 108. Now, y'all, I need to take the derivative. When I want a max or a min, we want derivatives. But I don't want to take the derivative of the volume right now because that's 3 different variables. Say the derivative of the volume with respect to x is fine, but I have x here, but I need to get rid of this h then. So if I take it back up here in this first equation and solve that for h, so I would subtract the x squared and divide by 4x. That's what h equals. We're going to substitute that in here for h. A set of x's would divide. We then could finish off our distributing and so forth. And I would end up with 27x minus 1/4 of x to the 3rd. So I want the maximum volume. Remember, maximum ends up happening when the first derivative is 0 or undefined. So I take my first derivative. When does that derivative equal 0? So I could add 3/4 x squared over to here, multiply both sides by 4, divide by 3, and then take my square root. So when I do that, I get my critical values of x equals plus or minus 6. So again, that would be timesing by 4, dividing by 3, which gives me 36. X squared is 36, so x is plus or minus 6 for the critical values. Now remember, for your first derivative number line, that's my critical values, 6 and negative 6. The first derivative, this was my function right here, is a parabola that opens down. A parabola that opens down, this value would be negative, positive, and negative. Or you could plug in negative 7, 0, and 7 into the derivative and see if they're positive or negative. So again, this first derivative is a parabola. It does open down. So negative value, positive value, negative value. So with that in mind, remember that a maximum would occur when a graph changes from increasing to decreasing. So my maximum value here is going to occur when x equals 6. So when x equals 6, I plug that into here to get the height. And that would be my dimensions of my box to give me a maximum volume. I would need a box of 6 by 6 by 3. All right, it says which points of the point on this graph, y equals 4 minus x squared, are closest to the point 0, 2. Well, here's a graph of a parabola. There's the point 0, 2. So the distance from here to a point on the parabola, that'd be the same distance from here to a point on the parabola because that point 0, 2 is on the line of symmetry. And so the distance formula, the distance would be then this x value minus the 0 squared plus y minus that y value of 2 squared, and then the square root of that. So that's my distance. Now, if I want the shortest distance, then I actually want to know when what's underneath that square root bar would be the smallest value. So in reality, what I'm really looking for is going to be when underneath here, when its derivative is going to be a minimum. Now, where did this red come from? If I was to substitute back in, because I don't want to take the derivative with a d, an x, and a y, that's 3 variables. We don't want to do that. We only want 2. So remember back at the beginning, the y equals 4 minus x squared. So we plug that in here for the y, and that's where this 4 minus x squared came from. All right, and again, I could go ahead and FOIL these out, combine the like terms, and this is what we get underneath there. So for the smallest distance would be when this whole thing is the smallest number. For it to be the smallest number would mean what's under the radical bar to be the smallest number itself. So I could just take the derivative of what's underneath the radical bar to get my critical numbers. So 4x to the third minus 6x, greatest common factor is 2x. So my critical values would be x is 0 or x equals plus or minus the square root of 3/2. First derivative number line. This is an x to the third graph, which ends going down and up. So this down, this would be a negative value. It's going to come up and cross through here and then back up. So again, that is going to, it's going to go like this, down and back up for x to the third graph. So this value is negative, and positive. None of these had a squared value. That doesn't, because that actually is a difference of squares. Okay, so each of those x's only count once in your roots there. All right, so again, it was negative, and positive. We are looking for the smallest. That means we want the minimum. A minimum will occur when a graph changes from decreasing to increasing. So the original function here is decreasing to increasing. So there would be a minimum at that. And again, decreasing to increasing, there would be a minimum at this one as well. So again, you would then plug those two x values into the original function, 4 minus x squared, and that's how you will get your y values there. All right, the minimum area. So we have a rectangular piece of paper. It's to contain 24 square inches of print. The margins are at the top and bottom of the page are to be 1.5 inches, and the margins on the right and the left are to be 1 inch each. What should be the dimensions of the page to have the least amount of paper to be used? So again, we want 24 inches of print. So what's in yellow is 24 inches. The margins at the top, okay, and the bottom of the page are 1.5 each. So this is an extra 1.5 here and 1.5 here. And this is an extra inch going across and across. So you have an extra inch on the right and the left. So if I said this paper here was x and this paper was y, well then this across the top would be y plus 2, and this across the bottom would be x plus 3. So that's how I got the dimensions here of x plus 3 times y plus 2 to equal the area. Now, the piece of paper, the yellow print, is x times y is 24, because the rectangular page is to contain 24 square inches of print. And there was your margins. So I need to solve for either x or y here and solve it and plug it into the other equation because I want to have the least amount of paper. So I do need to have a derivative to find the minimum. So I solve for x or y. I did y, and I went ahead and plug 24 over x in for this y up here. FOIL that out, and here's your equation. Take your derivative. Set your derivative equal to 0. I'll get x equals plus or minus 6 for the critical values. So for my critical values, I had 6 and negative 6. Right here, x can never be 0 in that original function. So that was part of my domain there. X cannot be 0. Now, I need this 2 minus 72 divided by x squared. I need to know if those are positive or negative values when I plug in the numbers. So let's say I plugged in 1. That would be 2 minus 72 divided by 1 squared. Well, that would definitely be a negative value here. If I was to plug in, say, 10, that would be 2 minus 72 divided by 100. 72 divided by 100, okay, because that would be the 10 squared. Because again, this is the values for the derivative, remind you. Okay, so I didn't really worry about these negative ones because I can't have negative amount of paper. All right, so again, plugging in 1, that would be 2 minus 72 divided by 1. I think I said that wrong a minute ago. I'm sorry. 2 minus 72 would be a negative value. Plug it in, say 10. 72 divided by 10 squared would be 72 divided by 100 would be 0.72. So 2 minus that 0.72 would be a positive number. So right here is where my minimum would occur for my original function. Because remember, this is telling me on my original function, my graph is decreasing from 0 to 6, increasing from 6 to infinity. So I would have a minimum at x equals 6. If x equals 6, then y equals 4. If x equals 6, this was 6 plus the 3, so that height of the paper would have to be 9. Y was 4. 24 divided by 6 gave me y is 4. 4 plus the 2 gives me 6 for the other dimension. That ends 3.7. I wish you the best of luck on these. Just take your time with them. We're not in a hurry. You really need to make sure you understand them. You guys have a great day, and we'll see you tomorrow.